Hello students, this is Anjana from Computer Science Department. In this class, I am going to discuss about NAND, NOR and other two-level implementation gates. Now let's get into our topic. So these are our topics about the NAND and NOR implementation and other two-level, how we are going to implement it in other levels. So these are the basic logic gates implementation by the universal gates here. These are the we are going to discuss about mainly here the basic logical gates implementation by the universal gates and the Boolean function implementation by the universal gates and about the wide logic and non-degenerate forms. Next in this topic we will discuss the following things about the NAND and NOR implementation. Here how we are going to implement the basic gates using the universal gate and the implementation of the Boolean function using the universal gates here. See what is a universal gate here. A gate that can be used to create any logic gate, we can say it as a universal gate. Okay, hence the NAND and NOR are the universal gates. So we can say the NAND and NOR gates also as a universal gates. Why? Because these gates are used to create the logic gate. Yes or no? By using these gates we are going to generate a boolean by using the by using a boolean expression we are going to generate a logic gates here. Here for that logic gates we are going to use the for to implement the logical gate we are going to use the NAND and NOR gates. So from this we can say that NAND and NOR gates are the universal gates. So any boolean function can be created, any boolean function, whatever the boolean function, that any boolean function can be created using the AND, OR and NOT gates. So whatever the expression, nothing will be dependable on the expression. Here whatever the expression, that expression can be that boolean function can be created by using the, obviously it can be created by using the AND, OR and NOT gates. Here the AND, OR and NOT gates can be implemented by using the NAND and NOR gates here. So see, this is the implementation of NOT using the NAND gate. Okay, how we are going to implement the NOT by using the NAND gate? Now let us see in this picture. Here in the NAND gate, here this is a NAND gate. Okay, NAND gate means of this is the AND gate, and for this IN gate this is the little circle. If the little circle drawn in front of the NAND gate, we can say it as a NAND gate. Okay, sorry, if the little circle drawn in front of the AND gate, we can say it as a NAND gate. So this is the NAND gate. Okay, uh, a NAND gate with single input acts like a NOT gate. See here, how many inputs are there here? Only one input. So we can take this one as a NOT gate. Okay, actually the symbol of the NOT gate is this one. So without if the NOT gate is not available for to design a circuit, then a NAND gate with single input also can be considered as a NOT gate. Okay, so then how we are going to implement this and using the NAND gate? See here this is the AND gate. Here you are having this here the AND gate with two inputs we have taken. Here as a NAND gate is the invert of the AND. Here what they are saying is a NAND gate is the invert of AND. So by putting an inverter on the output of the NAND, we can give the AND gate. See here this is a NAND gate, this is the NAND gate. Here without this circle we can say this as AND gate, this one is a NAND gate. For this inverter, if we are giving the NAND gate as a input, so we can say it as a uh, we can say it as a AND gate. Okay, we can use it as a AND gate. Okay, if to design a circuit we are not having some AND gate, we are having only inverter and we are having only the NAND gate. From this, if we connect at the output part of, if the inverter is connected at the output part of the NAND gate, so from that we can use it as a AND gate. Okay, this is how we are going to implement the uh, AND gate using the NAND gate. So that is from the NAND gate we are going to implement the AND gate. See how we are going to implementation of OR using the NAND gate. See here, by putting the additional inverters in the input, we can achieve an OR gate by a NAND gate. See, this is basically by using the De Morgan's law itself, we can implement that. So here, if it is, if you are having two NAND gates and one OR gate, if you are having only NAND gates, we need the OR gate for to design a circuit. Then the not NOR gate, sorry, OR gate is not available to design that circuit. Then finally, what you have to do, by putting the additional inverters in the input, from that we can achieve a OR gate by a NAND gate. This is basically this is basically implemented by using the De Morgan's law itself. Why? Because in the De Morgan's, from the basis of the De Morgan's law itself, we are going to know that how we can design this particular OR gate by use, how we are going to implement this particular OR gate by using the NAND gate. See here you are having two NAND gates. For that, see, by putting the additional inverters in the input, see, this is the inverter symbol. Here this is the symbol, we are having the symbol, no, this is the inverter symbol. In the previous slide we have observed that at the output of the NAND gate, see, output of the NAND gate, we can have the AND gate. See, this is the output, we are having the inverter. Okay, from this we can use the AND gate. Here in this slide, these two are the NAND gates. From the input beginning itself, an additional inverter is used. From this we can use OR gate. Okay, from this we can use two NAND gates with inverter is a combination. From this we can implement the OR gate. This is how we are going to implement the. This is how we are going to implement the OR gate using the NAND implementation. See, basically, the implementation is not a major task to achieve. But if it is not available, if it is available, okay, we can easily design the circuit. But in case of if it is not available, in that particular case, we are going to do this type of applications that such that we can easily find out the solution to that particular problem. See, by using the De Morgan's law, on the basis of the De Morgan's law itself, we have constructed this particular type of circuits. See, what is the equivalence? What is the symbolic equivalence of the NAND gate here? See, this is a NAND gate. It is having some 3 inputs. So, for AND we have to use a multiplication operation. So, x, y, z whole dash. This is the NAND gate, and this is the OR gate. Okay, this is the OR gate. That is, it is giving the input x, y, z. So, OR gate means we have to perform the addition. So, x naught into x naught plus y naught plus z naught. So, this is how, from the De Morgan's law, we can say that x, y, z whole dash is equal to x dash plus y dash plus z dash. So from that also we can construct the this is also same. In place of this NAND gate, at the time of that we can use this OR gate also. See, by what they are saying is how it is the symbolic equivalence of the NAND gate. See, um, by the De Morgan's law, we can describe the NAND gate graphically by using this following symbols. See how we are going to implement the NAND gate by in the 2 level. See, when it is a 2 level implementation of the NAND gate, the implementation of the Boolean function with the NAND gate requires that the function can be simplified into the sum of the products form. See, it is the sum of the products. See here, this is the sum of the products. That is, A into B is one product, C into D is another product. Here we are not having any products, but that okay, fine. Here we are going to sum the sum of the products. Okay, then A into B means for that we have to design the circuit like this. A into B means for that we have to design circuit like this. This is AND gate. So A, B is the input. C into D means for that we have designed the circuit like this. This is C into D. Next one E is the normal thing. For that we are going to apply the addition operation. So this is one input and this is one input and this is one input. By taking these inputs we are going to draw the OR gate. Why? Because we are going to perform the addition operation. No? For that we are going to draw the OR gate, and this is the final output that we are going to get. Final expression that we are going to get in this two-level implementation of the NAND gate. Okay, this is how we are going to implement the NAND gate. See here, basically the implementation of the Boolean function with the NAND gate requires that the function to be simplified into the sum of it should be simplified into the sum of the products form, not into the product of sums. It should be simplified into the sum of the products form. Whenever it is simplified, then it will be easy to construct the circuit. Otherwise, it is very highly difficult task to construct the circuit. See how what is the function implementation by the NAND gate. Here the following is the above implement. This is following is the implementation of the NAND gate here. This is the above functional implementation of the NAND gate here. Here it is taking the two inputs, and by taking these two inputs here, it is going to implement here. See how we are going to implement this NAND gate. This is NAND gate. See, so A into B whole dash, C into D whole dash plus E dash. See, for that also we have implemented the NAND gate. This is the final output. But here A, B, C, D, E. Here E will be dash. So A, B whole dash plus C, D whole dash. Then the result outcome will be A, B whole dash plus C, D whole dash plus E. Plus E dash. This is the resultant outcome for this particular circuit. If it is the sum of the products, then it will be easy to find out the problem to that particular solution. So that may not be a difficult task to perform here. So by simply observing these things, so we are taking this as a this can be implemented by using the NAND gate. So without using the NAND gate also we can, if the NAND gate is not available, by simply placing the inverter in front of the AND gate, we can say it as a from simply keeping the inverter in front of the AND gate, we can use it as a NAND gate. These are the from this we are going to construct the combination circuits here. But based upon these things also we are let us know how we are going to perform these operations there. See, if for a single input, the NOR gate acts like as a NOT gate. See, in the previous slide also, in the last slide also, we have discussed that how it will be implemented as a single input NOR gate acts like as a NOT gate. Here this one is a NOT gate and this one is a NOR gate, but for a NOR gate it is not having the multiple inputs, it is having only one input. So we can consider that one as a NOT gate. Instead of using NOT gate, we can if it is a NOR gate like this, if it is a NOR gate having one input, instead of using that NOT gate, you can use this NOR gate. When we can use that NOR gate, if it is having only one input, okay, instead of using NOT gate, if it is having only one input of the NOR gate, then we can use it as a NOT gate. Okay, See how we are going to transmit the AND gate by using this De Morgan's law. By the De Morgan's theorem, putting two extra inverters in the input, we achieve the AND gate by using the NOR gate here. And here by the De Morgan's theorem, putting the two extra inverters into the input, we achieve the AND gate by the NOR gate. So that is the AND gate, and these are the NOR implementation of the AND gate. So by using the De Morgan's theorem, putting the two extra inverters in the input, we can achieve the AND gate by using the NOT gate. So this one is the AND gate, and this is the NOR implementation of the AND gate. This is the AND gate, and this is the NOR implementation of the AND gate. Okay, observe. Did you observe the difference between AND gate? If you observe difference between AND gate and the NOR implementation of the AND gate, so that is the thing. So how we are going to implement the OR gate? If it is OR gate implementation of by using the NOR gate, as a NOR, it is the inverter of the OR gate. So by putting the inverter in the input of the NOR, we can get the OR gate. So if you observe this figure, if you observe this figure, as an OR, it is the inverter of the OR gate. So by putting the inverter in the input in the output of the NOR, we can get the OR gate. So if you observe, this one is the NOR gate and this one is the AND gate. So it is having two inputs, okay, two inputs, but it is not having any front and back, and it is not any dependable circuit. So simply by asking them ask them to get into the picture, she is not ready to do that, but it has to do the task. Finally it This is how we are going to implement the OR gate by using the NOR gate. Okay. Here the NOR is the inverter of the OR gate. So by putting the inverter into the input or the output NOR, we get the OR gate. This is the OR gate, and this is the NOR implementation of the OR gate here. So by this is a NOR gate. In front of the NOT gate, OR gate itself, it has placed the NOR gate. So from this we can get the OR gate. See how we are going to graphical equivalent of the NOR gate. See, this is the first one is the AND gate, and second one is first one is the OR gate, and second one is the AND gate. So we can write it as x plus y plus z whole dash. We can write it as the x dash y dash z dash. Why? Because uh, before itself it is having not, after before itself it is having not. So we can write it as a x dash y dash z dash. We should not write it as a x plus x dash plus y dash plus z dash. Why? Because before itself it is x plus y plus z. After that we are going to apply the not operation on that. So it is x dash plus y dash plus z dash. Here the operation is here. This is a NAND gate, and here we are having some logical inputs, that is x, y, and z. From this we can write as x dash, y dash, and z dash. From this we can write it as x plus y plus z whole dash. what is the two level implementation of the NOR gate? See, two level implementation with the NOR gates requires the function should be simplified. First of all, it should requires the simplified function into the product of sum form. For example, it should be like AB dash plus A dash B into C plus D dash. See how what is the AB dash means it you have to take the AND gate here. A B dash, this is for A B dash, ఇది A dash B. For that, this is the sum of the products. For that, you have to use the OR gate here. We have designed the circuit for this expression, and next we have to draw the gate for this. This is the product of sums. A B dash plus A dash B into C plus D dash, that is product of sums, no? Then for that product operation, what you have to use? You have to use the AND gate. So for these two we have drawn AND gate, and next one, this is the C plus D dash. C plus D dash means that one is for C we have taken as it is a simple C. Simply we have taken the simply we can take in the this C like that, but for D dash it took be in another way. So that is not an illuminating task just like that, but if it is implemented uh, just like that, we have to do the subproduct of the sum in the form such that it requires the functions to be it should be simplified. The two level implementation should be an OR gates requires the function should be simplified into the product of sums. For example, we have already seen the example. This is the example how we are going to connect using the NOR gate. Okay. Next one, now we are going to discuss about this the second topic, the two level implementation. Here we will discuss the following things. Discuss the following things in the that is wired logic and non-degenerate form. So we will discuss the following things in this topic, that is wired logic and non-degenerate form here. See, the NAND and NOR gates are widely used in the integrated IC means integrated chips. For that chips, we have to design for the combination circuit, no? So NAND and NOR gates are widely used in the integrated chips. So and next thing is a few NAND or NOR gates allow the wire connection between the outputs of two gates as is for specific functionality. So not for the input also, but for also at the output also some of the users will use at the output of these two gates for some specific functionality. We can say that wire connection as a wired logic. Through the wire we are going to connect one circuit. From that we can say that one as a wired logic. See what is a wired logic gate here. A wired logic gate does not produce a physical second level gate. It definitely does not going to produce a physical second level gate. So it is a wired connection. For this discussion, we will assume the following circuits as a. For this discussion, we will assume the following circuits as a two-level circuits. So, a wired logic gate does not produce a physical second-level gate, and it is a wired connection. So, for the discussion, we will assume the following circuits as a two-level implementation. We can assume the following circuits also as a two-level implementation. For that, it is a wired connection. A wired logic gate does not produce a physical second level. Definitely it does not produce a physical second level gate, but sometimes it should be a wired connection. It should not be a dependable task. It should be a undependable task such that the wired logic gate does not produce a physical second level gate. And next one, for the discussion we will assume the following circuits as a second level as a two level implementation gates here. See what is a open collector TTL and NAND gate. Open collector is a thing that we are going to use in that some electronic equipment, such that it is not a those are not a basic things that we are observing. The basic things to follow is here. Here you have to take the approach of the TTL, that is the transistor logic. By using the transistor logic itself, we are going to perform the task. Here the most common example and the viral logic by the NAND gate is the open collector itself. And when open collector TTL says that it is a TTL NAND gate, it should be used as a observe logic. But simply we can do the AND gate should be drawn within the lines going through the center of the gate. So the most common example for the AND wired logic by the NAND gate is the open collector. So from this we can say that the AND gate is drawn within the lines going through the center of the gate. Next one, it means that wired AND gate is not a physical gate, but only as it is a symbol to describe the, what is this? It is a symbol to describe the functionality done by the wired connection. So the following logic implemented by the circuit, we can say it as a AND or invert function. So it should be called as A into B dash and so on. So from this we can write like that, a into b plus c into d is equal to a dash into b dash plus c dash into c dash plus d dash. A dash, from this we can say that, see, this is a function a into b whole dash and so on to c into d whole dash. From this we wrote like, a plus b plus c plus d whole dash plus a dash plus b dash into c plus d dash. So this is a open collector. This we have in this we have already said what is a TTL, transistor transmission line. So this is a NAND gate and this is a ECL gate. ECL stands for emitter coupled logic. Here the NOR inputs of the emitter coupled logic is a gate are tied together to perform the OR function. So the following function implemented by circuit is known as a plus b whole dash plus c plus d whole dash. So this is the emitter coupled logic. This is the emitter coupled logic. So the NOR outputs of the ECL gates are tied together to perform the wide OR function. So from that the following logic can be implemented by circuit is called as a OR and invert function. So a plus b whole dash plus c plus d dash is equal to a plus b into c plus d whole dash. From that we can store, but that is a highly risk task, that some other thing we should not perform like that. So by using the center coupled logic, the NOR outputs of the ECL gate are tied together to perform the wired operation. So that is not a small thing. So from that the following logic can be implemented by using the circuit is called what is the following input. From that we can write the output is called as that one. So from this we can write like, so this is the ECL gate. This is the non-degenerate form. Suppose there are 16 possible combinations to have two-level forms, and 8 of these are degenerate form because they degenerate to a single operation, and the remaining 8 are not degenerative forms. So these are the non-degenerative forms. These forms are implemented in the sum of the products form or the products of some forms, that is AND or NAND NOR, OR, NAND, OR and NOR, NOR, NAND and NOR operations. The first gate listed in the each of the forms is a constitutive first level, while the second gate constitutes the second level. See, AND OR is the constituting first level, and OR and is constituting the second level. That is, the majority of the people are using these type of non-degenerate forms. So the first guy listed in the each of the forms is the constitute first level, while the second gate is the constitute of the second level. While the second gate is the constitute of the second level. See, this is the AND or invert implementation. These two forms NAND and NOR are equivalent. Both performs the AND or invert function. So the AND or invert implementation requires the expression of the sum of the products form. The following function is also implemented, that is F is equal to A into B plus C into D plus E whole dash. So this is the AND or invert implementation. This is one gate. This is one circuit. This is another one. By using the AND and NAND gate here, this is AND gate and this is NOR gate, and this is these two are NAND gates. This is NOT gate and this is AND gate. Okay, this is the AND or invert implementation. So, finally, the AND or OR and invert implementation is the OR and the NAND and the NOR or OR performs the equivalent operation. Both perform OR and AND invert function. So, the OR and invert implementation requires the expression in the product of sums form. So, the following function is implemented, that is A plus B into C plus D into E dash. Okay, this is another thing. So, this is the circuit for the OR and invert implementation. Okay.